Welcome back, guys. I'm your host, and today we are exploring ad hoc inference in AIOS, a game-changing feature that combines smart model selection with direct execution in a single API call. So, if you loved our previous episode of router in the AIOS ecosystem, then the natural next step is to do an inference with that router, right? So, this tutorial is for that, and for people who have not watched this tutorial, the previous tutorial of router, we will be going through some of the basic concepts for that router again, related to the router again. And for those who have already gone through it, I would request you to skip to the inference part as well. Okay, so let's get started. So don't forget that the router, it just selects the best model based on the query that you are passing. You still need a second API call to do the actual inference, right? So this ad hoc inference eliminates that friction entirely. In a single query, it does both the selection, finding the best model, right, as well as performing the inference. It is like ordering the best pizza in town as a query, and you don't worry about which restaurant, what is the rating, the number of user ratings, etc. But you are having the pizza delivered straight away to your door, right? It's like that. So we have this block diagram here. Let me explain that first. Okay, it's a bit big here. So let me open it in another tab. Yeah. So, so this is the first stage where we are giving some set of criterias to the ad hoc inference serving, and the criteria goes like I want the model to have a use case like chat completion, and it should support streaming, and the benchmarks in MMLU or the ARC should have at least 80 or 90, more than 80 or 90 as the accuracy, and the uptime should be at least greater than 10 hours. You can also pass tokens per second as greater than 10. So if you notice that these are some of the metadata, the top three are the metadata, whereas the bottom one is a live metrics. So we can pass both the metadata as well as live metrics to this ad hoc inference serving. So the blocks after filtering, so we will be getting, let's say out of n blocks, we have based on these filters, these 4 blocks are selected, right? The GPT-4, Claude, DeepSeek, and Mistral. Then we will have a custom policy, the decision making policy, which let's say based on certain weightage and for certain criteria, it decides that after doing some logical operations, some calculations based on the output, based on the input that the policy receives, it is selecting the DeepSeek model which is having the lowest score. And here the lowest score is given the higher priority. That's the logic, right? So then the final DeepSeek model is what is used for inference, right? So let me go back to the notebook. So for more details related to this ad hoc inference server, I request you to check this link. It has the entire details about all these requests and how they are filtered as well. You can also check some of the under the inference server registry. You can also see the necessary details and some of the APIs to do this inference serving as well, right? And let me so we should not forget that this ad hoc inference serving is a 2-stage step. One is the router, which is used for discovering and selecting the best blocks, and then the final block that is selected is then used for the inference, right? So that's what the summary I have here. Receives a single request containing both a selection query for the router and an inference data payload. These details I will show you in the payload, and it internally calls the router to find the best block based on the selection query and automatically forwards the data payload to the selected block and returns the final inference result to the client. So this is the overall flow here. And again, so before we do the actual inference, let us see some of the building blocks that is required to do this single API request such that the selection and discovery and the final inference itself happens all together, right? So, so this tutorial we are having in 6 stages. First, I will show you how the policy that we created, a sample policy we have created, can be deployed, and how you can create a policy as well. And also the request structure, I'll show you the payload, and the execution flow, like how the how the requests are arranged, like how the router passes its output to the next block, and also the live inference I'll show. We'll do an inference and we'll see the logs of it, the monitoring logs, and also towards the end I'll suggest another LLM matching technique. Instead of our in the router we can have our custom policies, is what I was saying, but we can also have an LLM matcher itself to figure out the best block out of some n blocks, right? So that also we'll see. So let's start with deploying the policy. So for this we need to create, basically the policy deployment comes in 3 stages. First thing is we need to assemble the policy in a certain format, in a certain folder structure. Then we need to upload the policies to the to a certain bucket, and then as a third step we will be doing the registration of the policy. So now before we further understand how to assemble the policy, let us not forget that we have all these we are proceeding with these steps with the assumption that we have a policy already created. So I have this code folder. The folder structure for the packaging the policy is we need to have a code folder. In that code folder we need to have a function.py, which is where the custom policy is defined, and the requirements.txt, like request or a gRPC or any library that you want, right? You can add the packages necessary. So here I have already implemented a custom policy. So here what it does is, based on the attributes that the user passes, right, it will select which block to use. So let's say, let's not forget this block comes here in this part of the block diagram, right? So it receives some n inputs. The first, let's say there are initially 100 blocks. Out of those 100 blocks, some 50 blocks are selected by the filters that we supply. Then the next set of the final selection of that one block, right, that will happen in this particular policy block. So we are discussing about this policy block now. So here the assumption is already there is one set of filtering happened. So in the second set of filtering, we can have a custom policy. So here, for example, I have a custom, let's say in this custom policy I have an attribute called cost saver, which will understand that if the model's parameters are less, right, so it will give priority to that, meaning so that we can avoid the excessive cost in doing inference for in a huge models, right? And similarly the GPU total memory, probably the models with less number of billion parameters will have lower memory as well. So that is an indication as well. Similarly, we can have a high quality lane as an attribute, where the end-to-end latency is used as a parameter, and the end-to-end FPS and also the MMLU score if you want better quality, right? So based on certain categories like this, we can do a final selection. So this is the custom policy that I was talking about. And we can also have a weighted combination of these optimization steps as well. Like you can say, I want 50% of cost saver and 50% of high quality lane, right? So now with the assumption that we have this policy in place, let's proceed. So with that in mind, let's say I'm creating a requirements.txt file. And so basically I have this function.py and requirements.txt file created in a code folder. So let me run this cell. You can see that it has basically prepared that necessary structure for us. And now let's proceed to the creating the zip file. So since now we have the folder structure, now we want to upload it to a certain location, and the upload format is a zip file like this, where we will create a zip with the policy name that we want, like attribute based router, right? And then probably these checkpoints can be ignored, and then this zipped file, right? The attribute based router is what we will use when uploading it. So this file path, the file name that you are seeing, attribute based router.zip, it will upload this file to this particular location, right, at this particular point. So the path, since I'm running the Jupyter notebook in the same path, I'm giving the path as the same. So let me run this cell. Now you can see that it is saying the file is saved to a certain location, right? So this is important because then only the AIOS ecosystem knows where the it has a certain we have defined certain paths where we'll be looking to get these zip files. So the next step is to register the policy. All we have done is just upload it, but we need to register the policy. So what is registration? So basically registering here refers to saying that I have this policy attribute based router and the version is 2.2 and the release tag is stable and the code can be found in this location, right? That's what I mean by registration. And apart from that, it also has a few other parameters that you can see here, right? For example, the policy input schema, the policy output schema, and the metadata of the author, right? And policy settings schema. So here I'm passing the metrics base URL because in my function.py, the custom policy that I have defined, I have to use a metrics URL to access the live metrics to take some decisions. That's a possibility, right? So that's why we are passing the parameters. We are giving the type of the parameter, we are giving a description, and we are giving some pattern for understanding here for the parsers as well. And here there is a policy parameter schema. Again, we are defining the same. Maybe we can also override it, right? And we have a selection query where we'll pass certain parameters like the let's say optimization goal. I was explaining to you certain tags here, right? Cost saver, high quality lane and all. So it refers to that. And what is the type of that optimization goal? It's an array, and the selection query is an object. So that's what we are defining here. And similarly, we can have other different kind of settings, policy settings, and the parameters as well. So for more details on this, I would request you to refer the AIOS V1, the OpenOS documentation on policies system, right? And this policy that we have implemented here, again, let's not forget there are different policy types in AIOS system. I will also add a link here. And the function.py that we have added, right, it actually belongs to a type 1 policy system where the actual execution happens within the AIOS this component itself, this structure, this application itself, right? So there are different policy types, and there are some policy types are long running cron jobs as well, right? So here we are using a type 1 policy of AIOS. And in the links I will share, you can also see there are you can also see many examples of this kind of registrations and different schemas and sample policies also. And the next thing is to now do the actual registration. All we have done till here is we have performed the preparation, the initial preparation. Now we are going to do the actual registration, for which I'm going to call this particular endpoint, basically a policy endpoint, and the registration payload is here. With this, I'm going to call the payload, right? Let me run this. Okay, I haven't defined request. Just a second. Okay, I have this. I forgot to run this cell. I think that's the reason. Let me run this cell. Yeah, now if I run this, yeah, now you can see the policy is created successfully, right? Okay, now let's move on to the actual ad hoc inference request structure. So here actually I can run this request via a curl command for using this endpoint, v1 infer endpoint. but here I will be running this with the Python request package. So as you can see here, the payload, it contains, the model is empty, meaning we are not specifying any particular model to be used here. And I also have a session ID here, which is 99, and the sequence number is 1. And the model parameters, in general, most of the models use these kind of parameters. And it has this temperature, top P, max tokens, which are generic parameters for all the models. So here the mode is also chat, and so the query is explain about the DeepSeek LLM model. So and also the selection, we have a selection query here. This selection query is different from what is defined in the policy. This selection query is part of the ad hoc inference serving request. So here we have the policy URI. So before that, of course, we define the header, which tells what is the parser that it needs to use, which version of the parser template that it needs to use. Here it is defined as parser v1. And the match type here is block. We are filtering the blocks. And the policy URI that I have given here is attribute based router 2.0 stable. This is same as what we registered here, right? Attribute 2.0, attribute based router 2.0 stable. So, and here we are passing the filter rules. We are having two. So first of all, we have a block query, which is responsible for filtering the components based on the components metadata. So here you can see I'm using a logical operator and the use case, I'm accessing the use case field of the LLM model's metadata, and I'm saying it should be like chat completion. So like is a operator that is allowed in this particular policy and the filter rule, and support streaming is also enabled. And apart from this, I also have a nested logical operator OR, where we are saying the MMLU score should be either greater than or equal to 80, or the ARC challenge score should be greater than or equal to 90 for the model. So this is the metadata related filtering, which is passed via the block query. We also have live metrics related query, right? So that's the advantage of this particular single request, right? So here we are saying the live metrics, the uptime hours should be greater than or equal to 10 for the model that we want to choose. And the LLM tokens per second should be greater than 10 here. So, so basically the policy, the filter understands that it needs to fetch the live metrics for each block. To do this, it takes the average of those blocks, all the instances of each block, right? So a block can have multiple instances, and it takes the average of each it takes the sum of all the instances divided by the total instances, which is nothing but the average. So it selects the best block based on that, and here it is based on the tokens per second. So this is the first level of the filters based on the metadata and the live. Here it is the metadata, and here it is the live metrics. Then comes our custom policy that we have defined. We are giving a user query as a find, reliable, and high performing chat model. We can use, as part of this custom policy, this particular query can be used like a similarity matching or domain classification or a entity classification kind of things. And here we also have the metrics based URL, because my custom policy that I have written here, it requires this to understand it requires this to understand the metrics of each block. So we are providing this URL, and this selection query, which is which is a parameter within this particular policy, right, that I am defining here. So that is responsible for we are giving some optimization goals, like, so that is responsible for using this particular weights. So for example, fast generator, this mode, it has to be 90%, whereas the free block has to be 10%. So this is the weighted average that we are doing, right? So this is the payload structure of the ad hoc inference serving policy. So here I have run the inference, and it has selected the Llama 4 Scout 17B block, and the session ID is session 99, and the sequence number is 1, and it is giving a reply. DeepSeek is an advanced artificial intelligence model designed to process and understand human language. It's part of a broader category of models known as transformer based models. So out of all the live blocks that it is running, it has selected this particular Llama 4 Scout. So let me also show this output in the Grafana logs. So here you can see in the Grafana logs, I just ran now. So basically the filters that we passed, right, it comes as input here. The ARC challenge, MMLU challenge, support streaming, it comes as input here, and all the blocks are live running blocks are fetched, and as you can see, the number of candidates block received is 4. So it has basically received the DeepSeek model and Gemma model, and then I think it has received the Quen model and also the Llama 4 Scout model. So it starts getting the live metrics, it calculates the scores. You can see that it is normalizing and calculating the score and all here. And the scores, the live metrics includes this kind of LLM tokens per second and live LLM active sessions and all. So in it has given a score, like the final score for DeepSeek is 4258, Gemma it is 6851, for Llama 4 it is 95, and for Quen it is just 0.05. So based on this, it has selected that the final block is Llama 4 Scout, and the score is 0.095, right? So that's the final block, and that's why we are seeing the inference, the model getting assigned is Llama 4 Scout here. I will also show this particular block's inference. So here I have this Llama 4 Scout 17V block. So let's say if I have this AIOS dashboard, I can get this via all the running pods. So here I have it. Sorry, this is the executor. Let me have the instance here. Yeah, if I go to the instance, you can see that the session is 99 and the sequence number is 1. You can see the same response. DeepSeek LLM is an advanced artificial intelligence AI, right? So basically the initial set of filters have been applied, and there are 4 models, candidate blocks out of it. And from that 4, that one model that has been selected is Llama 4 Scout 17V block, right? And yeah, so just before we conclude, I'll just give some some more things related to this custom policy. So earlier we had a deterministic token, we had a attribute based policy for this routing. We can also have some LLM based policies as well. So for an example, we can tell the LLM, based on the following user query, select the best block from the candidates provided. So, and the user query, the query string is nothing but what we pass here. Find a reliable and high performance chat model. In the non-LLM case, we can use this for some other similarity matching and other things. But in the user query, related to the LLM, it can be used in a much more as a natural language way, right? And we can pass either all the candidates to the LLM and ask it to return with one block ID as the best candidate. Or maybe to have more control and to be a bit more deterministic, we can also summarize the candidates we received by in a JSON format by getting the MMLU score or the capabilities, the tokens per second, certain based on certain criteria, and then pass that data to the LLM as the candidate and ask it to select the container image of the best candidate, right? So that is one possibility as well, and things get interesting when we use an LLM also. So I would request you to try a policy with an LLM, even a non-LLM approach as well, right? And so I think that's the end of the tutorial. So it's more or less like saying, in simple terms, I can say I want the best pizza in town, and you don't have to worry about what the user rating, the best possible combination of cost and all, the distance and all. So the query is the best pizza in town, and you will get the pizza delivered to your home. Thank you.